Okay, we are continuing our discussion on why the wind blows the way it does. Remember, we determined that pressure gradient force says that wind always blows from high pressure to low pressure. That's the first rule. And we had talked about the Coriolis force, which says that in the northern hemisphere, winds are always going to turn or veer off to the right, and they're always going to veer off to the left in the southern hemisphere. We're talking about friction right where we left off, right? And we pointed out that friction is greater down near the surface as wind blows because there's drag as wind and the Earth's surface, come into contact with one another. So wind blows slower down near the surface and there's less friction high up. We talked about how the air blows around high pressure and low pressure because of the Coriolis force up aloft. That's what we call a geostrophic balance. The balance between that pressure gradient force and the Coriolis force means that air just spins around, right? It blows clockwise around high pressure and counterclockwise around low pressure in the northern hemisphere, and the opposite of that in the southern hemisphere. Now, for us down here at the surface, because winds blow slower and because of that friction, we don't just see the air spin around the pressure systems like we do in the upper atmosphere. What we see down here is sort of a combination of all of these things. At the surface, air blows from high pressure to low pressure. That's an important rule to remember, right? Because air always blows from high. It never blows to left. In the northern hemisphere, okay, and that's sort of where we live, so it's sort of where we'll focus on. As air blows from high pressure to low pressure, remember, it's not going to cross these isobars at 90 degrees because it's going to be veering off to the right. And when we say veer off to the right, you think about you're in a car that's driving from high to low, right? If I'm driving from high to low, I'm going there. If I'm in the northern hemisphere and I'm veering to the right, that means I'm going to go this way, right? So that air, as it goes from high to low, blowing outward from high, it's going to veer off and go to the right, okay? Now, this is what happens right around the high pressure system. That wind blows inward to the low pressure system, and as it blows inward to the low, remember we blow outward from high, inward to low, we're going to veer in this way. Now, some of you are probably looking at this, hopefully, and thinking to yourself, now wait a minute, that arrow is turning to the left, doesn't it? And remember, at the if pressure gradient force was all that was mattering, then the wind would be crossing these isobars at 90-degree angles, right? But because of the Coriolis force, it's actually pushing the wind outward. So even though the general trend of the arrow is this way, that's because it's blowing from high pressure to low pressure. The air is being pushed outward because of the Coriolis force. If you look at the angle at which these lines are crossing the isobars there. So don't let that curve of that arrow make you think that this is somehow breaking the rule of the Coriolis force, because it's actually not. Okay? So this is generally what we see happening around high pressure and low pressure at the surface in the northern hemisphere. Now, when we look at a weather map that has isobars on it, we'll notice that sometimes the bars are farther apart from one another, sometimes they're closer together. And in terms of these gradients, what that means is that the distance traveled to get from high pressure to low pressure going this way is less than it is going this way. What that means for us on the ground, feeling that wind movement, is that the wind speed is going to be faster when these bars are closer together. Okay, when the bars are farther apart, that means the wind is going to blow slower. When they're close together, that means that the wind is going to be blowing faster. Now, when we look at a weather map and we see these big blue H's and these big red L's on the map, what we're looking at are high pressure and low pressure systems, right? Because it's not just the way that the air moves isn't just happening in one place. It's and on the surface of the earth, there are multiple high pressure systems at any given moment, multiple low pressure systems. They're all interacting with one another. So we say this is a high pressure system or a low pressure system, or we could say that a low pressure system is a cyclone and a high pressure system is an anticyclone. Okay. We can call them either high pressure, low pressure, or anticyclone and cyclone. They both work. In the northern hemisphere, like we mentioned, up aloft where there's little friction and there's geostrophic balance, in the northern hemisphere, winds blow around a high pressure system going clockwise and around a high pressure system going around a low pressure system going counterclockwise. In the southern hemisphere, it's just the opposite of that. Okay. So if you can remember how it is in the northern hemisphere, just remember how it is. It's opposite in the southern hemisphere. Around a high pressure system going counterclockwise, around a low pressure system going clockwise. Now, for us at the surface, what we are interested in is looking at, because the surface is of more concern for us because this is what we look at when we see a weather map. Around in the northern hemisphere, winds move outward from a high pressure system and veer to the right, and they blow inward towards a low pressure system, again veering to the right. Okay, otherwise they would just blow straight in from high to low, but that wind is being pushed outward to the right, even though the arrow makes it look like it's blowing to the left. Okay, and again, it's just the opposite of that in the southern hemisphere. So I pulled up one of my favorite websites. It's called windy.com. Just windy.com, and oh my gosh, this thing shows you so much cool stuff. So we can just look here, and what we're looking at is the little arrows that you see blowing around. Those are tell us wind direction, and the colors show us well, I think wind speed. Let's see, my screen isn't big enough. Let me see here. See if I can change it. Yeah, that's showing us wind speed. So if we look at the way that these little arrows are blowing here, we see that this is a counterclockwise motion, and it's blowing inward. It's kind of like when you flush the toilet, right? The water comes down and goes around and goes inward down the hole, right? So if you were to see something like this, where the wind is blowing in the northern hemisphere, the wind is blowing counterclockwise and inward, this is a low pressure system, isn't it? Right? There are lots of low pressure systems we can see on here. Here's one right here. See, the wind is being funneled around in here, and it's going inward and inward. Low pressure system. Here's a low pressure system right here. There are lots of low pressure systems on here we could find. And if you ever want to try out these things, windy.com is a great place to go and sort of check out some of the things we're learning about. It's harder to see the high pressure systems on here because the temperature or the pressure gradients tend to be a little tighter together at the low pressures, so the wind speed is greater around those. But let's see if we can find a place where the wind is blowing outward and clockwise. So yeah, right here. Right, see right here. The wind is blowing outward and it's kind of clockwise. And the wind from this high pressure system right here, and it appears that there's another system right here. I think these all three of these little high pressure systems were part of one bigger one maybe a day or two ago. And that's not important. The wind is blowing outward from this high pressure system and going clockwise, and then it gets sort of swept up into this over here and then ends up going. If pressure were the only thing that mattered, the wind would go from here straight to here, but it can't because the Coriolis is pushing it out and off to the right, which is here, and pushing it to the right here, right? And then we know that the friction is causing this to happen because this is what's happening at the surface. So if we keep in mind our pressure gradient force, our friction force, and our Coriolis force, those three things kind of determine which way the air moves from high pressure to low pressure. And I will provide you with the link to windy.com. It's really just windy.com. I don't know that I need to provide you with the link. So up until now, we've just been looking at the way the air moves at the surface, right? But we know that the atmosphere extends up into the sky, right? Many, many miles. So what happens when you have a low pressure system that all of that air is moving into? Like right here, the air is moving into that. Well, what happens when all of that air converges there? I mean, it can't just, at a certain point, that air comes in and reaches that low pressure system. And when it converges, there's only one thing it can do. It can't go down, right? It can't go down into the earth. So it converges and it goes up. At a low pressure system, air rises, right? Air rises up into the atmosphere. At a high pressure system, where air is coming out, when that air blows out, more air has to replace it, right? You can't just have a vacuum of no air there, right? So when air is blown out of a high pressure system, that air is replaced by air that sinks down, right? So at a low pressure system, air is rising. At a high pressure system, air is falling down. Now, let's think about what happens as air, what happens in terms of temperature in the troposphere as we go up in our hot air balloon, air cools down, right? So as air rises, it's going to cool down. As air descends or falls, it's going to warm up, okay? So what that means is that at a low pressure system, what we will usually see, or what we'll almost always see, is that as that air cools, right, that air converges and goes up into the atmosphere. As it cools down, what happens to the relative humidity? Because cold air can't hold as much cold air can't hold as much water vapor as warm air, right? So as that air cools, relative humidity gets greater and greater and greater, and at a certain point along here, that air temperature is going to cool down to the dew point temperature. You remember that? The dew point temperature is the temperature at which air is saturated and can't hold any more water. Well, if that air continues to rise, it's going to continue to cool down. And if the temperature falls below the dew point, that means that some of that water vapor in that air is going to get kicked out. It's going to condense and it's going to come water. And that's where we start to see clouds. If there's enough moisture in this air, that's where you'll get storms and things like that. But this is where you'll get precipitation. You only see storms and clouds, big storms associated with low pressure systems. When we think about high pressure systems, what we're looking at is air descending. And as air descends, it can hold more and more water vapor, right? So you don't see any clouds associated with a high pressure system because the air that is associated with it is getting warmer and is falling, is descending. So with a low pressure system, we see cloudy skies and potentially storms. With a high pressure system, you see blue, sunny skies. It doesn't necessarily mean it's going to be warm because you can have a high pressure system in the winter too. But if you have high pressure, you're not going to see any clouds. You will see sunny skies. So we will stop there and we will pick it up in the next lecture.